This section is on properties of light. What is light? We can just start with that. Light is oscillating electric and magnetic fields, and if you wanted to draw it, you could say, we could draw the light as a wave, say like this, so on. Maybe I'll make that a little more like this, right? And so this would be the electric field that's oscillating up and down while the light is traveling this way. The light's going that way, the electric field's oscillating up and down as it's going. While that's happening, there's a magnetic field perpendicular that's going into and out of the board. I don't know if I can draw this very well, but like that. And so if you're looking at the magnetic field would be oscillating this way. And so while the electric field is in the plane of the whiteboard, the magnetic field is going in and out of the whiteboard. And so this is the thing I would call B, and this is the thing we would call E, right? And so that's a picture of the electric and magnetic field. The speed of the travel is 3 times 10 to the 300 million meters per second, or about 186,000 miles a second. That's, the moon is 240,000 miles away, so it takes a little more than a second for light to get from here to the moon, from Earth to the moon. The sun is about 93 million miles away. It takes about 8 minutes for light to get from the sun to us. So under that scenario, if someone were to steal the sun and run off with it, there would be 8 minutes go by before we noticed. It turns out there's a definite ratio between E and B. It turns out that in light, the magnitude of the electric field is equal to the speed of light times the magnitude of the magnetic field. And so if you take the ratio of those two fields in a light wave, you get the speed of light. Not only that, but you might remember the constants. Epsilon naught is equal to 8.85 times 10 to the minus 12th Coulomb squared per Newton meter squared, and mu naught is equal to 4 pi times 10 to the minus 7 Tesla meters per ampere. It turns out that the speed of light, c, is equal to 1 over the square root of mu naught times epsilon naught. So these are sort of constants of the universe, and so is c. So if the electric field in a light wave is 3.85 times 10 to the minus 3 volts per meter, we can ask what's the magnetic field, and we just said, what's the magnetic field? B, we said on the previous screen, we said E equals C times B, and so B is equal to E over C, which is 3.85 times 10 to the minus 3 volts per meter divided by 3 times 10 to the 8th meters per second, which is equal to 1.28 times 10 to the minus 11 Tesla. And just to do a unit check on that, you remember to check the units, the Lorentz force was F is equal to QVB, right? Where that's newtons, so the units is newtons is equal to coulombs times meters per second times Tesla. And so a Tesla is equal to a Newton second per Coulomb meter. And so a volt is a joule per Coulomb, and so it's a Newton meter per Coulomb. And so if I arrange this, if I substitute this in for volts, the meters cancel, and I get Newton per Coulomb over meters per second, which is what I would get if I substituted this out. And so I get Tesla for this guy. So wavelengths vary in waves from 10 to the minus 15th meters for some gamma rays to really the shortest wavelengths we see, there's no limit, but the shortest wavelengths we see are wavelengths that are around 10 to the minus 15th meters for light waves. That's the size of an atomic nucleus. Those are very tiny, very high energy. The longest wavelengths we see, 4 million meters is 4,000 miles, maybe 2,000 miles more like. Anyway, somewhere in there, 2,600 miles. So that's a really long wavelength. But we see the whole spectrum in here of wavelengths, right? If you remember, since it's a traveling wave, the formula for waves is the speed of the wave is equal to the wavelength times the frequency, right? And since all light travels at c in a vacuum, where c is 3 times 10 to the 8th, like we said on the last screen, meters per second, then we can say, look, the wavelength and the frequency are related by the frequency is equal to the speed of light divided by the wavelength, for example. And so we can look at this range and say, we can ask the question, what's the frequency range for these two guys, right? And so F is equal to 3 times 10 to the 8th meters per second divided by 10 to the minus 15 meters, and that's equal to 3 times 10 to the 23rd hertz, right? Where it's just the meters and the meters cancel, it's just 1 over seconds with it, which is hertz. So I don't know what the word for this one is, but this is, 3 bajillion hertz, right? Similarly, we could do the other one, and we could say the frequency for the other one is 3 times 10 to the 8th meters per second divided by 4 times 10 to the 6 meters, and that gives you 0.75 times 100, or 75 hertz, something like that. That's a wide frequency range, of course, just as you have a wide wavelength range. All of these different frequencies, of course, and wavelengths have significance for areas of science or technology.